Muy bien. Okay. Hello, and thanks for being here with us for the final part of the workshop today. So, Christina, it's your time. Go ahead.
Thank you. Okay, I'm gonna share my screen now. And let's see. Then I hope that all of you were successful creating the RR array and the plot theta versus RR. Then please send me your plots if you have finished, or if you have questions about the coding. Also send it to me, and I will try to help you. I just realized that maybe for this part of the code in which I'm computing the distances, I'm just using a function in IDL, but I'm not sure if you are familiar with any function in Python to do this. I mentioned one in the workshop too. Then try to use that one. But in the case that you are having problems with this, for now you can just compute the distances in Cartesians. Then it's just I just want to make sure that you understand the algorithm, and then when you have more time, you can check what is the best function in Python to compute distances over a sphere. Then I just wanted to mention that point. Okay, so we have created our DD vector, and we have created our RR vector. We have our theta vector. Then we are almost done to compute the correlation function for this catalog. Then the last step that we have to make now is to normalize the arrays DD and RR. Because we need to do this to compare apples with apples. Given that normally the random catalog is much more larger than the data catalog, obviously we will have more number pairs per bin, but we need to normalize the things to really make a fair comparison. The way in which you have to normalize this is just dividing by the number of pairs, the total number of pairs. Then the complete array will be divided by the same amount. And in this case, it depends on how you computed your DD and RR vector. If you were following what I did, then you should normalize using this formula here, because this is just the total number of pairs that you will have. Then if you didn't follow what I did, and instead you count the distances twice, for example, and you compute, for example, the distance between the galaxy A and galaxy B, and then you again repeat the galaxy B and galaxy A, then the way to normalize is this one, because this is the number of pairs. Of course, the number of pairs in that case is higher because you're counting 2 times. And actually, this is the normalization that I put in the lecture, in the equations in the lecture, and that is what I normally find in the books, because that is not thought in code terms. And then I guess that is why they just normalize using that in the books. But in our case, we will normalize by this factor here. Then I'm going to do that now. And then normalize the DD and RR vectors. And this is very simple. I will write, well, DDN will be my normalized vector, will be DD over ND, which is the number of data, the number of sources in my data catalog times ND minus 1, and all of that divided by 2. I'm going to make sure that I'm doing this correctly. Yes, I'm just will add this. This is annoying in IDL, but it's always better to specify that this is double. And yeah, that's it. And I repeat the same thing for the RR vector. Then the RR vector will be RR, and here I use the number of elements in the random catalog. I think I defined in R before, didn't I? Yes, I defined in R before. Okay. Okay, and now that was the normalization, and now we are gonna make the step number 4, and we will use the more basic estimator to compute the correlation function, which is dd over rr minus 1. This is, I mentioned before that this is the very basic estimator that should give more or less the right answer, but could have some problems, specifically at largest scales. But for now, we will just use this to check if we get a power law at least. Then computing the correlation function. This is the natural estimator. Omega, I will call this L because this is my low mass for the low mass sample. And this is just dd normalized over rr normalized, and I subtract 1. Okay, then this array should contain the final answer to our initial problem. And now we will make the plot. We have to make a log-log plot of theta versus omega theta and check that this has a power law shape. And I'm gonna make the plot here. I have this already done. This is just to define the file for the plot. And here I choose the limit for the plot only. Then in the XY, I'm plotting from 2 arc seconds until theta max, and in the Y-axis, I'm plotting over those values. Then plot theta begin. Yes, this is again between 0 and -2, but it depends on how you define the theta vector, and omega L between 1 and -2, because the same reason that I explained you before, dd and rr contain 2 extra beans in the extreme, in the last and first position. Okay, then this is the type of point. X range will be the one that I defined here. Then just and the Y range will be YR. I'm gonna make sure that this is in logarithmic scale, Y and X axis. What else? I think that is all. I was just put X title theta, Y title omega theta. Okay, then this should work. This will again compute all the distances. But that don't take so long, then we can just run this again. Okay, done. That was fast. Let's check if the plot makes sense. This one. Okay. This is the final measurement. This makes sense. We have, of course, some fluctuations because the statistic, but more or less this has a kind of a power law shape, then that is good. Yeah, and that's it. Then now you can be able to compute clustering using any catalog. As long as you have the random catalog and the data catalog, you can just compute clustering. Then, as I said, this is not the best estimator to use. And also, we only have points here, and we are missing one important part, which is to include error bars. Then that is actually the next step in the workshop. But now I'm gonna give you some time, then you can work in this part of the code. And also I'm gonna print here the value of omega L. Then I can provide you this information to you when I upload this in the web page. Again, you don't have to consider the last and the first beam here. But yeah, that is what I was expecting you to make. I will leave you now for 10 more minutes, and I will be back soon. And hopefully you can compute this and send me the plots of your first correlation function computation. Okay, I'm gonna stop sharing, and if you have any question, I'm gonna be here, and I will be back in 10 minutes to finish the last part of the workshop today. Okay, I'm back for the last part of our workshop today. I'm gonna now compute the error bars for the measurement. That is pretty easy to make. Then in 5 minutes, I'm gonna show you how can you make it. Okay. Okay, we are doing now point number 6, in which we will add error bars. Then in this case, we will just assume Poisson error bars only, just to simplify the things. That is fine for now. And this means that the error in omega is given by this equation here. This is just the Poisson error. I also provide this equation in the lecture 2. Then you can double check there. Yes, and here DD is the not normalized array, because for Poisson errors, you're taking the square root of the number counts. Then the normalized value is not informative at all in this case. Then to do this, I will just then normalize, to define the omega L, the error, then add error bars. Then this error will be simply the square root of the DD vector, not normalized, divided by RR normalized. But I always, after to compute the square root of DD, which is the Poisson error bars, I have to then normalize by the same factor as before. Then I'm gonna copy this here. This is the normalization factor. Okay, then I also have to normalize this after to compute the square root by the same factor. Then now we should be okay with the error bars. I'm gonna make the plot to include the error bars. Then I'm gonna use the same plot as before, but now I'm gonna add the error bars. Then plot error, the same as before. But now the third argument in my case will be the error that we just computed. Again, in the position okay. I think that should work. Yes. Yeah, I'm just gonna define this for a better visualization. Okay, now I'm gonna run the code and check how our measurement looks with error bars. This take a little bit to compute all the distances again. Okay, this is done. And there we go. Then this is our correlation function. Then now we have error bars included. Then this point that was kind of shift from the power law has a larger error bar too, then that makes sense. And that's it. This is the measurement that we have for our catalog. Then I hope that you can also make your own code to reproduce this measurement. I'm gonna upload. I'm gonna stop sharing now because we have just 1 minute left. Then I'm gonna upload all what we did today in the web page again. Then you can check the code and the plots that we got. And I'm also be uploaded the output of our code. Then in case you are really lost, you can use the DD and RR terms and the theta term, the theta array, to just plot the correlation function and play a little bit with the estimator. Then you can find that in my web page. I'm gonna upload this now. And the final part of the workshop, we will do this tomorrow. We just have the final part of the workshop is just to run the code again, but with the other catalog. Then you don't have to make so much coding to complete the workshop. But I'm gonna do that tomorrow at the beginning of the workshop and show you the result. And that is very nice because we will be comparing the clustering of the two different catalogs. Then we will check if they have the same clustering or differences. Then that will be very nice, and we can make some interpretations too. Then I hope you can join us tomorrow for that part. And that's all for today. And hope to see you, all of you, tomorrow for the lecture 4.
Okay, thank you very much, Christina, for sharing your time and your work with us. Sorry, and for you, our visitors and people that is assisting to this course. We hope you to see you tomorrow and be connected to AstrotWin to 2020. Okay, so see you tomorrow.
See you tomorrow. Thank you.
Bye.
Bye.